Thank you, everyone, for coming today and for your patience. I'm really, really happy. We have Professor George Perrett here talking to us today on machine learning methods, combining Bayesian machine learning approaches to causal inference. Professor Perrett is very talented. He has a multidisciplinary background in psychology, applied statistics, and public health. And he's someone who's very well versed in both the technical aspects of statistics and software development, and applying those methodological advances to substantive problems in educational and social science research. So he started his career as an applied researcher in randomized control trials, estimating causal effects on various educational interventions on reducing educational inequalities. But I think he's now, in addition to that, is also looking at causal inference within observational contexts. So, I was reading through some of the research that they've been doing. It's really wonderful that not only have there been these technical advances in using sort of Bayesian methods to try to solve some of the issues in making causal inference in observational studies, but also making it accessible for people who are not quite so advanced in programming on statistics. So I myself am very much looking forward to his talk. So I hope you will enjoy it as well.
Well, thank you for the warm introduction. Excited that. All right, so thank you for the kind invitation and the kind welcome. Really excited to be here and talk about some of the work that me and my team are doing at New York University. Let me just turn this off so it's not going to keep popping up. All right. So for today, I'm going to be using a running example. So suppose that a well-known sports company created a new high-performance marathon shoe, and they released this product with the claim that if you wear this shoe called the Hyper Shoe, you're going to run a marathon faster than you would have run had you not worn the shoe. And this is an inherently causal question. It asks, is wearing the shoe actually what's causing runners to run faster? Or maybe there's some difference between runners that run with the shoe and runners that don't. So really, this is a good example of looking at how do we actually know if hyper shoes are what's causing the faster running, or if it's something else. And so before I get into some of the methods work that I work on, we're going to have to start by thinking, what does a causal effect even mean? What does it mean when we say X causes Y? An educational program causes better test scores, or a medicine causes alleviation of symptoms for an illness. So this woman is Helen O'Beary, finishing the New York City Marathon in 2023. She won, and she is actually wearing these hyper shoes. These are a real product. I've changed the name for brand protection's sake, but she won the race and she wore these hyper shoes. And so if we want to know what is the causal effect of wearing hyper shoes on Helen's running time, we have to ask ourselves, what would her time have been had she been wearing a different pair of shoes that didn't have this new technology in it? Causal inference is oftentimes phrased as a comparison between factual and counterfactual worlds. And what I mean by this is there's two potential outcomes. There is the world in which Helen wore the shoes. That's what we observed. And there's this world in which Helen didn't wear the shoes. These are often denoted as Y1 and Y0. In this case, Y1 is Helen's time with the hyper shoes. That's what we actually get to see. And Y0 is what Helen's time would have been had she not worn the hyper shoes. And the treatment effect, the causal impact of the shoes, is just the difference between these two numbers. Now, this assumes that it's a binary treatment. You either wear the shoes or you don't wear the shoes. There's generalizations of this. If you look at multiple things, maybe there's a competitive company that makes their own technology. So it's traditional shoes, paper shoes, and hyper shoe plus. So this all generalizes up, but I'm going to be using a binary example today just for simplicity. And as I said, we only observe this factual world. So we see that Helen wore the shoes and finished in a time of 147 minutes, which is very, very fast. Using kind of the traditional notation of causal inference, variable Z generally is used to represent the treatment. So Z1 here is going to mean that somebody has the treatment, or the hyper shoes, and Z0 means they're just wearing kind of the traditional shoes. And so here we see Helen's wearing the shoes, and we observe her time with the shoes. Her time with the shoes is going to be denoted with Y1, and Y is which potential outcome we observe. Now, the fundamental problem of causal inference, the thing that we have to solve is we can't observe the world in which Helen didn't wear the hypershoes. We don't see what Y0 is. Here we only see Y, which in the case of Helen, maps onto Y1. And we oftentimes call this the counterfactual outcome. The counterfactual outcome is the outcome that we don't see, but we need to see in order to estimate a causal effect. So what can we do about the fundamental problem of causal inference? Usually when I speak to particularly social scientists about this, this is actually not a problem at all. There's a pretty easy solution we have. How can we know how fast Helen would have run? Well, after she finished the race, we could have her return to the start line and rerun the race, but this time without the hypershoes. Now, I'm sure some of you might already see the problem with this. Running back-to-back marathons is very fatiguing. If she ran slower without the hypershoes, it's impossible for us to distinguish if it was because of the different shoes or if it was because she was very tired after just running a marathon. So this approach isn't really going to work for us. Now, some people might say this is a little ridiculous, like we're not expecting her to just turn around and rerun the race. Something more reasonable might be we could have her run another marathon without the hypershoe a few months after the race. So we're going to wait a longer amount of time, and then we're going to have her rerun the marathon, this time without the shoes. So this, on its surface, may seem a little bit more appealing, but there's still a lot of issues. The weather could be different. There's actually many things that could be different. Maybe Helen changed how she was training. Maybe she got an injury during this time in between the first marathon and this hypothetical second marathon. And so in this world, it'd be impossible to distinguish if the impact of the hypershoe was because of the hypershoe actually making a difference, or maybe a change in training, change in injury status, change in the weather. So for all of these reasons, this approach doesn't really work. And because of all this complexity, the individual causal effect, knowing how well the hypershoes worked for just Helen, if we only are looking at Helen, is generally considered impossible. We can't really quantify it. Statisticians or mathematicians would call it a non-identifiable estimate. So we seem kind of stuck. The fundamental problem of causal inference is really big. It's a huge problem. How do we move forward? What we can do, instead of looking at a single person's causal effect, is we can think of average causal effects. Now, an average causal effect is, what if we had a bigger group of people? Maybe we can think about how well the hypershoe works on average across this group. So instead of looking at just Helen, imagine we look at the 150 runners in the professional women's category of the New York City Marathon. And so now we see we have a whole bunch of runners. I'm only showing the first few, but imagine this goes all the way to 150. And for each runner, they either wear the hypershoe, some of them wear the hypershoe, we see a few Z equals 1, and some of them don't wear the hypershoe. Notice that the third row and the fifth and sixth row here have a Z0. That indicates that they are not wearing the hypershoe. And so we have a mix of different potential outcomes. For some runners, we observe Y1, and for other runners, we observe Y0. And so what we can do is we can actually use this information to estimate average causal effects. Now, there's a few different types of average causal effects that I just want to introduce before I really start getting into the actual estimation process. The most famous one, and really the most straightforward to think about, is the sample average treatment effect. And so what the sample average treatment effect is we're going to take our sample of 150 women, and we're going to say, well, what is the average of all the individual treatment effects? So remember, the individual treatment effect is each person's Y1 minus Y0. We're just going to average over all of these things. This is just the mathematical notation for just taking an average. It's just the mean. Sometimes this looks a little scarier than it actually is. Very simple computation. But something I want to point out is we still can't directly observe this quantity. Notice that Y1 and Y0 are in the state. And we can't observe Y1 and Y0 for each person. That would require some kind of magical ability, being able to simultaneously observe somebody with the shoe and without the shoe, because people can only wear the shoe or not wear it. We can't directly see this quantity. We can only estimate it. So the fundamental problem of causal inference still applies here, and we could say that we can never know the true value of the state. What we can do is we can estimate it. And so I'm going to be using some language. Whenever I say something like the true state, that is a quantity that we can't directly observe, but we'd like to observe it. And when I talk about estimating the state, that means we're going to use statistical methods to impute this missing data. Causal inference is really a missing data problem. And all we're doing is trying to fill in these question marks. And once we fill in these question marks, then we can take the mean. So every single statistical method out there from the for causal inference, at least, from the most simple to the most sophisticated, is really just going to be plugging in some values for these question marks. And then we're going to be taking the difference between each of them and then taking a mean. And that's how we would estimate the state. It's a simple data imputation problem. Now, oftentimes in the social sciences, which is where I do most of my work, also in the medical sciences, sometimes we're not just interested in the average of a treatment effect across the whole sample, but maybe a treatment works differently for a different group of people. In my early work, I worked a lot of interventions that we had specific benefits for students who were low performing. So maybe treatment education, we expect to work better for low achieving students than higher achieving students. In this example, maybe the shoe works better for really fit athletes, essentially the best runners, and maybe it works a little bit differently for lower performing athletes. The slower runners, that is. And so the conditional average treatment effect, we could think of it as the expectation of y1 minus y0 given some value of x. And really all this means is we're going to be looking at something very similar to the state, but just for a specific group of folks. We want to know the conditional expectation of this difference given some value of a covariate, be it resting heart rate or in education, be it baseline test performance, things like that. So these are the two average treatment effects I'm going to be talking about today. Think of SATE as how well does the thing work on average, and think of CATE as how well does the thing work for specific subsets of our data set. Okay, so that's kind of our background on causal inference, and now we're going to move into how do we actually do estimation. And this is the more interesting part. How do we actually get an answer? How do we know what the causal effect is, or how do we estimate it, I should say? So randomized studies use a combination of design and statistical modeling to estimate average causal effects. And whenever you have the opportunity to randomize something, you really should do it. They have a lot of really desirable properties. So suppose that we take these 150 runners in our sample that we've talked about. And what we did is we gave each one a 0.5 probability of wearing hypershoes. So for each runner before the race, we flip a coin. And if it's heads, they wear hypershoes. And if it's tails, they don't wear hypershoes. Then we give them the shoes they're going to run with, and they go off and run the race. And before this coin flipping took place, we also measured the resting heart rate of each runner. Why resting heart rate? It's a good proxy for general fitness. In this case, I also want to point out that resting heart rate is called a pre-treatment variable. In this case, a pre-treatment variable is any variable that does not have potential outcomes itself. Essentially, any covariate that theoretically could not be influenced by the treatment. Why am I talking about this? Turns out if you include information from post-treatment variables into your analysis, some really bad stuff could happen. It can really skew the whole results. So generally speaking, when I talk about adjusting for variables and models, keep in mind that I'm only really talking about pre-treatment variables. They're often called pre-treatment because if you've measured the thing before the treatment was assigned, it is just philosophically impossible, or epistemologically impossible, I should say, for the treatment to alter it because the treatment wasn't realized yet. So keep that in mind when I'm talking about resting heart rate. Now, randomized studies, they're not assumption-free. We make a few assumptions in order to use this design and any models within it. The most important is called the ignorability assumption. And so what the ignorability assumption means is that y1 and y0 have to be independent of z. Now that sounds very fancy, probably like if you've taken a course in probability, you might know what this means. But if you don't, think of it as we're assuming that the random assignment was actually random. Now, that seems kind of silly. If I've told you we flip coins, why wouldn't it be random? Turns out plenty of things could happen. The most common violation of this assumption is differential dropout. So say that we actually randomly assign the shoes, but for whatever reason, people that didn't get the treatment, people who didn't wear hypershoes, maybe they quit the race halfway through and they don't actually finish. And so they kind of drop out and we have missing outcome data. That could actually lead to a violation of this assumption. We might also see things like sometimes in education, randomization is actually implemented by teachers in these classroom interventions. Usually teachers are the ones actually delivering the treatment, and teachers really want their students to do well. And maybe if they believe that this treatment is actually a big benefit, they're going to maybe overprescribe. They're going to give the treatment to more students than they were supposed to. So this has happened in the past too. And so this is how this ignorability assumption can be violated, even in the case of randomized studies. So we're assuming that the randomization is pristine. We're also going to make an assumption called the stable unit treatment assignment, the SUTVA assumption. Statisticians have a bad way of naming things. It's not a field known for its simple naming conventions. And all this means is that we are assuming that one individual's outcome is not going to influence other individuals' outcomes. So if I'm running the race, or I actually said Helen's running the race, Helen wearing the shoes is not going to influence how fast one of her teammates runs. And so we're going to assume these two things. And here's some data from our 150 runners. Now, this is all simulated. It's hypothetical data, but this actually resembles what real race data could look like. Race data has a notorious nonlinear relationship between a bunch of covariates and the outcome. So we have minutes to finish the race on the y-axis. Lower is obviously better. And we have our resting heart rate, our single covariate on the x-axis. And I've colored each runner based on if they're wearing a hypershoe or not. So here, red indicates that you're wearing the hypershoes, and blue indicates that you're not wearing the hypershoes. So right off the bat, we see that the red points tend to be a little bit lower than the blue points. But we haven't actually estimated the treatment effect yet. And what I'd really like to draw folks' attentions to is some properties of the data right now. And so a really, really nice property of randomized studies is that they're said to have balance in expectation. And what this means is that if we look at X, there's kind of an equal number of resting heart rate across the treatment and control. So if we go over the x-axis, there seems to be an equal representation of blue and red points across X. And if I make a histogram of these two things, shaded by treatment assignment, we'll see that resting heart rate is very similar between these two groups. And if I take the means of each of these distributions, they're very, very close to each other. Now, I said in expectation, because even though these distributions are very, very similar, they're clearly not identical. However, if I had infinitely many data, if I had infinity runners, or if I redid this experiment infinitely many times, if you can imagine doing that, these distributions would converge and be exactly the same. And these means would be exactly the same. And so that's what I mean when I say in expectation. But this is a really, really desirable property. What this balance in expectation means is that there's really no difference between the treatment group and the control group for any covariates. And that is true for the ones we observe, like resting heart rate. That's also true for the variables we don't observe, like age, maybe years of experience running, maybe injury status. We know that all of those variables have this property too. Now, I'm going to do something a little bit strange. Let's pretend that we have this magical machine. We have some machine that we can go into, and we can actually go back in time. And we can go back in time to the moment right before the race and flip everybody's shoes around, and then have them rerun the race. And so all the problems I talked about at the beginning, let's just pretend that doesn't exist. And we use this magical machine, and we can see each runner's true potential outcome. So shaded in black is what would have happened to each runner had they not worn the hypershoes, or had they worn the hypershoes, basically the counterfactual value for each runner. Now, I've shaded this in black because this is not something we can do in real life. As I said, this data is simulated. This is the only reason I can actually do this. And I've also incorporated this information onto the plot. You now see these lines on the plot too. This is the true function that I've used to generate the data. And what this tells us is the shoe does work for runners with lower resting heart rate, but as resting heart rate goes up, the treatment effect starts to change, and all the way over here, the shoe is actually bad for performance. So for this entire range, wearing the shoe is good. It's smaller here than it is over here, gets bigger again, gets smaller, 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 and then it flips. So that is kind of the true relationship of the data. And I can say it's the true relationship because in this case, I'm kind of playing a game where I'm pretending to be this all-powerful creature that can actually see both of these worlds and actually generated the data. Unfortunately, in our own research, we can never do this. It'd be much easier if we could, but unfortunately not. So now that I've kind of gone back in time and seen each person's counterfactual value, I can plot each of their individual causal effects. And I can take the mean of all of them. So this is the mean. And that's how we get the true sample average treatment effect. So the true sample average treatment effect is negative 4.25. And what this means is that on average, for one of these professional runners, we expect you to gain 4.25 minutes of speed by wearing the hypersheaths. Now that's only true on average. The solid black line is the true conditional average treatment effect. And so that is how well will each runner do on average, given some value of resting heart rate. And so as we can see, it's basically below 0 for every value of resting heart rate until we get to about 53, and then it starts going up, and then it starts becoming bad. So runners with a heart rate under 53 beats per minute, the shoe is good for. Over 53 beats per minute, the shoe seems to be bad for. And not just seems to be, it actually is bad for you because this is the truth. So now that I've shown everybody the answer, keep that negative 4.25 in the back of your head. Let's try to estimate the SATE. So back to what we actually do as researchers, we don't have all potential outcomes. Here's the data we do observe. What can we do? Well, the simple thing is we could say, let's just take the average of the average outcome for all the people in the control group, and we're just going to plug that in for everybody in the treatment group. So for all these missing Y zeros, we're just going to fill in the average of the Y zeros we observe. And we can repeat this process for Y12. So I'm just going to take the average of all of the data I can observe here, and it's 167. I'm just going to plug that in for everybody. This is also called the difference in means. And so for those of you who have ever fit a t-test, this is actually what your t-test is doing. Use a t-test to estimate a causal effect and say a randomized study. And my estimated SATE is really just the difference between these two lines. It's just the difference, it's the difference between the red line here and the blue line here. And that comes out to be some number close to -4. I've put this difference right here as this point. Now, the good thing about statistical models is they don't just give us a point estimate, they also give us measures of uncertainty. And so I've computed a 95% confidence interval here. And what we see is even though the point is really, really close to the truth, which is desirable, there's a lot of uncertainty in our model. This 95% confidence interval is really large. And it's so large, in fact, if we plot 0 on the axis here, we see that our 95% confidence interval contains 0. And so if you're a frequentist, what this means is you're unable to reject the null hypothesis. If you're a Bayesian, you could even say that your credible interval has a high probability that the effect could be 0. And so we don't feel good about telling decision makers that they should go buy this shoe. And these shoes are very expensive. The real shoe is actually shockingly expensive. And so the results from these studies don't make us feel great about justifying that cost. So is this the best we can do? And I'm going to make the case, no, we can do something much better. We haven't used any information about resting heart rate. Notice that these lines right here, this is our statistical model, and it's doing a really poor job at fitting the data. Like if I said, here's our model, look at how it fits the data, we shouldn't feel great about this. We're missing, like these lines are not a good representation of what's happening with this relationship. So usually what we can do here is we can utilize what we know about resting heart rate. So resting heart rate, it clearly predicts the treatment, or it clearly predicts the outcome, I should say. Clearly predicts the outcome. And it also clearly predicts, I should say the outcome. Clearly predicts the outcome here. So linear regression is a common way to adjust for this. So how does linear regression work? We're doing something very similar to what we did with the difference in means. We're just going to incorporate information about resting heart rate. So here I'm going to fit a linear model by drawing these two lines, and this is the best linear fit to the data. And instead of filling in the averages, now I'm going to fill in predictions from my linear regression model. And so see here that each of these imputed data points shown in blue and red now has a slightly different number. Whereas for the difference in means, we use the same value for each person in Y0 and the same value for each person in Y1. Now we're using a little bit more of a sophisticated model, and we're going to try to get more precise predictions for each missing data point. So what happens when we actually use a linear regression as opposed to the difference in means? Our point estimate doesn't look particularly different. Notice that it's very close to the line still, but our uncertainty is notably different. When we adjust for information that is predictive of the outcome, we get more certainty in our estimation process. This is called efficiency in the causal inference world. Our estimates of the state become more efficient. And so now our 95% confidence interval, if you're a frequentist, does not cross 0, and we feel a lot better about recommending this shoe. So even though the point estimates are very similar, we're reaching a much different conclusion. And the takeaway from this is it's not just about the point estimate. We care about having results that are also efficient. We want precision in our estimation as well. And so just as a comparison, when we fit the data better, we're getting more efficient estimates. So keep that in mind. Now, this is still clearly not linear data. Like if we look at this, the lines fit better than they did before, but it's still violating the linearity assumption of linear regression. Yep. Yeah. Fitness. Yeah. The more fit you are, the lower your resting heart rate becomes. Yeah. So lower resting heart rate is like a marker of heart strength. Yes. The better runner you are, the lower your resting heart rate should be. Yeah. So for elite runners, this is what you'd see. So for like an elite runner, you'd see heart rate in like the 30s for like a true professional. Yeah. Yeah. So that's why these are really, really low, because everybody running these is really fit. Like I said, this is based on, it's not exactly real data, but it's based on real data that does exist. And this is what you'd see with actual professionals. Yeah. Same thing with the outcomes here. Like these, if you convert it to hours, you'd be like, wow, that's shockingly quick. But these women are running really, really fast. Yeah. Yeah. So is it a problem that we're violating the linearity assumption? There's a famous critique of this by a mathematician named Friedman, called Friedman's critique, where he points out that there could be some negative asymptotic properties of when you fit the wrong model, basically when you incorporate this information in regression. Now, there's a notable response to this by Winston Lin, where he says, well, with like sufficiently large samples, and sufficiently large is actually pretty small, these problems become easily solved. So I just want to put this in there that there have been some people that have challenged the idea of adjusting for things automatically makes your result more efficient. But there's also been some responses that says in the real world, like any studies we would all be running, it's not really a concern. So I just want to note that before moving on. So that's the case of randomized studies. Now, what we saw is both of those estimates of the state were really, really close to the line, and our modeling decisions really only influenced our uncertainty. That's not the case in the observational study. So randomization is not always possible, nor is it feasible, nor is it a good idea, particularly in things like education. We might be interested in understanding the causal effects of going to college on income, but it would be considered pretty unethical to randomly assign if you went to college or not. Like imagine taking the same students with the same college entrance score and saying, we're just going to flip a coin and determine if you go to college or not. That'd be a very unpopular idea. And so in education, observational studies are really common. Same thing in medicine too, even though you have to clear randomized trials to make drugs prescribed. Once drugs are on the market, it's really, really difficult to do randomized studies. And so comparing two medications that have both already passed clinical trials actually is very difficult and oftentimes involves observational studies. So suppose that instead of randomizing the hypershoe, the 150 runners self-selected to either wear or not wear the hypershoes. Now, when I was talking about randomized studies, I said we use kind of information from the design to get that nice balance property. And then we still use the statistical model. We still fit our difference in means. We still fit our linear regression. Here, the statistical model is going to do all the weight for us. It's going to do all the work. We don't have those design properties to help us out. And this is really important because confounding variables enter the equation. So because of randomization, we couldn't have any confounders. And why is that? It's because nothing was related to the treatment. So the definition of a confounder is it's any pretreatment variable that predicts both the outcome and the treatment. So when we randomize the treatment, we break the relationship between every confounder that could, or every covariate that exists or could exist, and the treatment. We know that there's no relationship between heart rate, between age, between experience, and the treatment when we randomized it. When we don't randomize it, there could be a relationship. So if there's a relationship between the treatment and the outcome, it's a confounding variable, and they can create all sorts of challenges. I also want to point out statistical significance tests should not be used to identify confounders. Just because there's no statistically significant difference between covariate between the treatment and the control does not mean that it's not a confounder. And that is, there's been a lot of work that suggested that. So keep that in mind. You can't really test if something's a confounder or not. So randomized studies, they don't have any confounding variables. Observational studies do. And that makes us have to do a lot more assumptions, or make stronger assumptions. So for randomized studies, we had this ignorability assumption where it was Y1 and Y0 independent of Z. So for observational studies, this becomes considerably stronger. And we call it the conditional ignorability assumption. And what this means is that Y1 and Y0 are independent of Z given X. Now, what is X here? X represents a matrix of all confounding variables. So it's basically any confounder that exists. We don't know what X is. It's just any confounder that exists. That is X. And so we are assuming that we have measured X and that we are appropriately conditioning for it. The appropriately conditioning piece is really important here. You could think of it as meaning that any model-based parametric assumptions are satisfied. What's a model-based parametric assumption? Seems kind of jargony. Things like the linearity assumption of linear regression, or the homoscedasticity of a regression. Those are what I mean when I say parametric assumptions. So we're assuming that we've measured every single confounder that exists and that we have appropriately modeled it. And so that's what the conditional ignorability assumption means. And when we are in an observational study, we are making this assumption. So what's the challenge? Well, in order to believe that we've measured all confounding variables, we generally need to measure a lot of things. We have to have a lot more stuff in our data set. But the more variables we include in our models, the harder it is to satisfy the parametric assumptions. So there's this challenge of, well, if you want to believe we've measured every confounding variable, that could be a lot of variables. It could be 200, it could be 300 variables sometimes I've seen in papers. But when we're adjusting for 200 or 300 variables, it becomes really, really difficult to make sure all those parametric assumptions are satisfied. Or even if we see that they're not satisfied, it becomes nearly impossible to fix it using standard methods like linear regression. So now let's imagine what things would look like in an observational context. So here's our 150 runners. Now they are not randomized. And so if I plot the resting heart rate for the treatment group and the control group, we'll notice these distributions are now much further apart. Remember, in the randomized case, they're right on top of each other. Now they're spread out. And if we compute the means are notably different. And so in this example, we see that runners that have lower resting heart rate are much more likely to wear the hypershoes. And runners that have a higher resting heart rate are much more likely to not wear the hypershoes. And if we look at this plot over here, we see that resting heart rate is pretty predictive of finishing time. So a lower resting heart rate means you're running faster. A higher resting heart rate means you're running slower. And that is because resting heart rate is a measure of cardiovascular strength, basically how strong your heart is. And people with stronger hearts are going to be running faster. Again, we're going to use our magical time machine to go back in time, flip everybody's shoe assignment around, and notice the relationship on this plot. It's the exact same, and the potential outcomes are exactly the same here. The only thing that's different is which one we're actually observing. We're going to do the same things before, get everybody's true individual treatment effect, take the mean. It's going to be negative 4.25, same number as before. So the state is unchanged here. It's because I haven't actually changed the Y's. I haven't changed the data generating process. I've only changed who's in the treatment and who's in the control group. So everything else is going to stay the same. Kate's going to stay the same too, where runners with lower resting heart rate benefit from the shoes. Runners with higher resting heart rates are harmed by the shoes. Just as a proof of what I was talking about, notice that the Y0 and Y1 columns are actually exactly the same. The only thing that's different is the Z's and the Y's. And because Z is kind of influencing which potential outcome we observe, that's why the Y is different. So that's why the Sates are the same. That's why the Kates are the same. The only thing I've tweaked here is what's called the assignment mechanism. It's the process of assigning the shoes to folks. It was randomized before. It's no longer randomized. So let's estimate the Sate for our observational study. Here's our data. We're going to start by doing the difference in means like we did before. So I can do the difference in means. Now these lines are really far apart. These lines are really far apart. And remember, the difference in means is ignoring resting heart rate. And resting heart rate here is a confounder. And is a confounding variable because, as we've seen, it is related to the treatment here on your right, and it's related to the outcome here on the left. And because I generated the data, I can assure you it is a confounder. Also, in this example, we're going to really simplify it. I'm going to tell you it's the only confounder. Because I've simulated this data, I know that it's the only confounding variable. In a real life study, you want to think about many, many variables. But everything I'm about to say generalizes to those cases as well if you've measured everything. So here's the difference in means. So now, if we actually take that average, if we do our t-test, we'd get an estimated causal effect of -20. So -20 minutes seems huge. What happens when we factor in the uncertainty? It's not covering the truth. So this dashed line is the true Sate. Our statistical model is just giving us the wrong answer. And this is because statistical models are biased in observational studies when we not adjust for every confounder. So we've not adjusted for resting heart rate here. And so my result's going to be biased. It's going to completely not contain the truth. And this is a bad thing. So we know that was wrong because we didn't adjust for a confounder. So usually in social science, when we're in observational studies, we'll adjust for confounding variables. So let's use linear regression to adjust for resting heart rate. So I'll fit my linear regression. These lines seem to be fitting the data a little bit better. I'll fill in my missing potential outcomes from this regression model. Now that I have a number for both Y1 and Y0, I can take the mean between each of those two columns, get a number for each person's estimated treatment effect, take the average of all of those. That's my estimated Sate. So my estimated Sate for my linear regression, it's about -8, -7, closer than difference in means. Let's see what happens when we factor in the uncertainty. And I'm still not covering the truth. So I've adjusted for every confounding variable, but now I'm still biased. So what's happening? Remember when I was talking about the conditional ignorability assumption, I said we have to measure and appropriately condition on. So we have measured and included here, but we have not done so in an appropriate way. And what I mean by that is, whoops, actually, let me go back. These lines are not fitting the data well. And because there's no balance between the two groups, because it's not a randomized study, I need the lines to rebalance the data for me. The lines have to be a good fit in order to account for the confounding variable. And because I fit the wrong model, because I've violated the parametric assumptions, in this case, the linearity assumption, I'm biased. So what can be done about this? How do we appropriately condition on confounding variables? This is why the propensity score matching and weighting literature became very popular. So propensity scores were initially introduced by Don Rubin. And the idea is we're going to try to make our observational data look like randomized data. So the idea of the propensity score is we're going to model for each data point, what is the probability of this being assigned the treatment, given all these confounding variables that we've measured. We can estimate this propensity score. Once we estimate the propensity score, we can basically re-weight our data set. So what I've done here is I've re-weighted each runner based on these propensity scores to try to make our data look more like a randomized study. Now, what's the problems with propensity score weighting and matching? There's a lot of what's called researcher degrees of freedom. So you still have to estimate your propensity score. Now, if you appropriately estimate your propensity score, then these issues that I've just been talking about are going to go away, but appropriately estimating your propensity score is an equally hard task as appropriately estimating the outcome. So that's the challenge of propensity score matching. But the theory is when I re-weight my data set, when I basically use the propensity score to weight up or weight down these individual points. So for example, see here, we have a whole lot of folks in the control group, and there's only one person in the treatment group. The idea is I'm going to weight up this person's outcomes. I'm going to make the influence of this person larger. And so when I adjust my data set with these weights, the means are now very similar again. And so if I look at the means, I have balance in means, meaning that the mean of resting heart rate is similar between the control group and the treatment group. And if we achieve perfect balance with our propensity score across every moment of the distribution, then we recover these nice properties of randomized studies. The challenge here, though, is even though our means look correct, these distributions still are notably different. They have a different variance. And when I say we have to balance every moment of the distribution, we don't just need to make the mean similar, we need to make the mean similar, we need to make the variance similar, and we have to make the covariance similar. And the variance and covariance are particularly hard to rebalance in a lot of cases. But let's just stop here. So I'm going to use this as my propensity score model, and I might look at this as I'm a researcher and say, the means look pretty good. This looks like they would look in a randomized study, so I'm going to continue. So after doing your propensity score rebalancing, you can fit a linear regression. And the idea is, well, this linear regression is going to be okay because I've rebalanced my data. I've now made my data look like a randomized study. And as we saw before, we could fit the wrong model for randomized studies and still get the right answer. And that's because I had that nice balance property. So I try to rebalance my data, fit a linear regression. So my estimated state looks a little bit closer to the truth, but I'm still missing. So I'm still biased even with propensity score matching or weighting. Why is that? It's because for this example, I've misspecified my propensity score model. Turns out the treatment assignment mechanism here is very, very complicated. It's very, very complex. Well, how do I know that? It's because I made it. But a lot of times the assignment mechanism is really, really complex. Like it's a really, really complex process of who self-selects to wear hyper shoes and who doesn't, or who self-selects to go to college and who doesn't. There's a lot of complexity, there's a lot of interactions. And if you don't appropriately model those things in and make a lot of parametric assumptions, this could happen. So the key points up until here is the difference in means and linear regression. They're unbiased estimators of the state for a randomized study. That being said, linear regression is more efficient than the difference in means because we're appropriately using our covariates. Now in the observational study world, the difference in means was biased because we didn't adjust for our confounding variable. And linear regression was also biased, even though we conditioned on all the confounding variables. And this was because linear regression violated the parametric assumptions. We did not appropriately condition on our confounder. So we conditioned on it, just not the right way. Propensity score weighting, in this case, IPTW, it did not fix the violations of the parametric assumptions. And that's because we did not have balance for every moment of the distribution. We had balance in means, but we did not have balance in variance. As an aside, when you don't have balance in variance, it generally means there's some nonlinear term that you haven't included. When you don't have balance in covariance, it generally means you're missing an interaction. That's like a rule of thumb, but you could still miss things even if you have really, really close looking balance statistics. So are we stuck? Are we destined to not be able to do observational studies? And I'm going to make the case that there's more advanced methods that we can use to simplify this process. And this is where machine learning for causal inference comes in. So what is machine learning? it could mean a lot of things. I'm going to start by talking about something called a regression tree. And so all machine learning means in the context in which I talk about it is we want a way to flexibly predict some outcome Y given some set of predictors X. So here's a clearly nonlinear relationship between X and Y. If we were to use linear regression, we'd have to get the appropriate nonlinear term. Maybe it's a squared term. Maybe it's a cubed term. Maybe it's a exponential function that I've done weird things to. Who knows? And you'd have to get that perfectly. So machine learning you don't need to know the function you're working with. It's just going to learn it. And so the idea of a regression tree is it's going to say, if I could only make one split in this data that would improve the fit, where would I make it? And so here it's going to pick 2.73, and it's just going to create two little groups. And for each group, it's going to take the mean. So the algorithm that does this, it actually searches every single possible break to make, and it picks the break that leads to the best predictions. Now, this is still a really, really bad prediction of Y. I think we can all see that, but the regression tree can keep going. So after making a first split, it can say, hey, I actually want to make a second split. What's the best second split I could make? And it can keep going and going and going. And it can make more and more and more splits. And the more and more splits it makes, the tighter it starts to fit the data. And so this is called a regression tree. It was one of the early versions of machine learning. Now, the problem with regression trees is it's still not a really smooth fit. It's still kind of jagged. And we also don't know how deep to make the trees. That's a problem we'll have to address too. So if I fit the regression tree to our data set, we can clearly model it non-linearly, but this fit still has a lot left to be desired. We can still fit the data much better than this. So this is the intuition behind a regression tree. We're just going to make these little chunks in our data, and each chunk gets a mean, and that's the prediction for that chunk. We could say that a single regression tree is non-parametric, and that it does not assume any linear relationship between X and Y. But the problem is it's still not very flexible. And flexible means we're going to really tightly fit all of our data points. The good news for us is that we can improve our predictions by combining many, many weak regression trees. Now, why do I say a weak regression tree? An easy way for me to get better predictions here is I could just keep making more and more and more splits in my regression tree all the way until I have a split for each person in the data set. And then I would perfectly predict my data, but it would poorly generalize to other data sets. So the machine learning literature has used this idea where we can make a weak regression tree, something like this, but combine a bunch of those weak trees to get a really smooth fit. And so that is what the algorithm I work with, Bayesian additive regression trees, does. So BART, it is a very, very flexible non-parametric machine learning model. It was initially introduced by Chipman, George, and McCulloch in 2007 and 2010. And it is a sum of trees model. And so what that means is we're going to have many, many, many small regression trees all the way up until M regression trees, where M is some number that researchers set to 75. And so what this means is our model is going to have 75 different regression trees. And here's the equation for the model. It's a little bit complex. You don't have to worry about it too much. The thing I want to draw our attention to is this G function. What is the G function? This is actually the Bayesian piece of the operation. So each tree is actually identified, like the tree, it is kind of selected. Each tree is shaped by a Bayesian prior, and it's also going to do what's called regularization. This is all done with something called the Metropolis-Hastings algorithm, the details of which are not important for this talk. But the regularization means it is going to protect our algorithm from overfitting, which is going to be problematic for us. So the Bayesian part of BART here, it is going to stop overfitting, and it is going to learn how to be really flexible, but flexible in a way that is not going to be detrimental to us. So that's the Bayesian component of our algorithm. Why do we like BART? It's really good at making predictions. So in the initial paper, they tried 42 different data sets. So they had 42 different data sets, and from these data sets, they made 840 what's called the train test split. And they compared BART to all the other top performing machine learning algorithms, things like neural networks, which are having a big moment now, something called boosting regression trees, something called random forest, which is a different tree-based method. And they saw how it did. And an important feature of BART is it works great off the shelf. So if you just use the defaults, it's going to work really, really well. That is something that's not true for other approaches, other machine learning approaches, I should say. And so what they found is BART performs slightly better than all the other machine learning algorithms when the other machine learning algorithms have been optimized. They did a ton of work to optimize all of the settings for all the other models, and then just use the defaults for BART. That's BART default at the top. And then BART CV is when they actually optimize BART, and it gets even better. So why do we like BART so much? It works really well, but requires very minimal effort by researchers. Works great off the shelf. So back to causal inference. How BART works for causal inference is we're just going to fit a BART model on all of our data. Once we fit a BART model on all of our data, we can take individual one's factual outcome, and we can flip their z around. We can say, hey, let's keep the resting heart rate the same, just flip this value for z, and use our BART model to get a prediction for what would have happened now. And we're going to repeat this process for every person in our data set. We're going to go all the way up to the 150th person, take their observed case, this person actually ran with the shoes. Whoops, we know what that is. We're going to say, what if they didn't run with the shoes? What if we flipped their z around and then used our BART model to predict what would have happened? So we're going to do that for everybody. And let's see what happens. Now, my colleagues and I at NYU, we've written an R package called BART Cause that does a lot of the complex Bayesian parts for you. So in a pretty simple R function, you can fit these models for yourselves. And we're going to fit our BART model, and here's our predictions. So we'll notice now that we're really tightly fitting the points. So for randomized studies, we have our nice balanced properties. We know that linear regression and difference in means are going to be okay. Let's look at how BART does. So here we have even more efficiency than linear regression. The uncertainty intervals are even smaller, and that's because we're fitting the data points really, really precisely. Those lines are not straight lines anymore. Now we can have curved lines. Now, something I've been ignoring so far is the conditional average treatment effect. And a problem I've been skipping over about linear regression and the difference in means is they predict the same average treatment effect for everybody. So if we used linear regression, we'd say everybody should go get the shoe. Now with BART, it'll actually give predictions for each person. And so we can look at each person and say, what would their treatment have been? So the black line here is the true conditional average treatment effect, and the purple line is our prediction from BART. And so what we see is we're not just performing well for the SATE, we're also properly modeling what's called treatment effect heterogeneity. So our BART model can not only get the average treatment effect correct, but it can also get the conditional average treatment effect correct. And that is something that linear regression and the difference in means are bad at, even in randomized studies. Now, what about the observational study space? This is where all of the methods we talked about have not been able to recover the truth. So here's our observational study data. We'll fit our BART model. Notice again, the lines are really tightly modeling the data now. And when we go back to our observational study results, we're now covering the true state here. So because BART is not going to make parametric assumptions, and because we're not having to make decisions about how to model the propensity score, like when you're fitting a propensity score model, you as an analyst need to make choices about which types of a model should you fit. How should you have interactions in your propensity score model? Should you have nonlinear terms? With the BART model, we don't have to worry about that. If there's nonlinearities, it's going to learn it. If there's interactions, it's going to learn it. And all this is being done without researchers making choices. And that is why BART is able to cover and the other methods are not. Again, even in the observational study context, we are estimating the CATE very well as the SATE. So we're still able to pick up treatment effect heterogeneity, even in the observational contexts. There's a whole lot of evidence for why BART works for causal inference. These are just a few that I've included now. So there's a long and growing list of research supporting this type of approach for the particularly observational studies context. And so what's the problem with BART? I've given my kind of spiel on why I think BART is really good and a really great thing to use. But working with BART for causal inference requires understanding a few different things. You have to understand the structural assumptions of causal inference. You have to understand some foundations of Bayesian inference, and you have to know how to program it all. Now, the structural assumptions we've already talked about. We've talked about ignorability in the randomized context and the observational context. Now, an important thing about this ignorability assumption in the observational studies world is you have to have measured the things and actually know that you have to put all of them into the model. There's some other assumptions we make to be relevant of time. I'm going to skip through these things pretty quickly. But BART cause, which is the package we use for fitting these BART models, it has a lot of hidden assumptions. And these hidden assumptions are that we assume people are going to use the thing properly. And that's a massive leap of faith. Turns out there's a ton of stuff that could go wrong. Even if we're in this ideal space where we know everything's been measured, people might not include variables in the model. They might not pick the correct average causal effect to estimate. And they also might just not know how to program. And these are all really big problems. And so what if we looked at a more realistic observational study, the types of things that we encounter out in the world? To evaluate how BART worked, our team actually had individuals come into our lab, and we asked them to estimate a version of the SATE, called the average sample treatment effect of the treated, for an observational study at a preschool program. We told them the outcome of interest was Y, scores on a verbal reasoning test. The treatment variable was variable Z, and that it was not randomly assigned. And we gave them 58 pre-treatment covariates. So if you wanted to fit a BART cause model, you would have to do something like this. You would have to know how to read in data in R, including knowing how file paths work. You would have to know how to index a data set, how to pick all 58 covariates, and you would want to include all of them. You'd need to know how to make it a data frame in the right way, and you'd have to know how to fit this BART cause call at the end. So this is all the code you'd have to fit to get the correct answer in our study. And it seems a little bit more complex, especially if you've never used this stuff before. Maybe you've never even used R before, and BART cause is only available in R. It's not in Stata. It's not in SPSS. So it could be a difficult time. You fit the model, and it'll estimate a result of 3.972. And so that actually is very close to the truth. The true result from this data set, I believe, is 3.98. So the result here is spot on. But you need to know how to program all of it. And so this is where Think Causal comes in. So a lot of my work over the last 2 years has been building a point-and-click software. So you can access these methods without any R programming at all, and with scaffolded educational pieces built into it. So if you don't know which variables you should adjust for, we built in learning modules where you could read about how to make decisions on including or excluding covariates. We built in learning modules on things like which average treatment effect should you select. So all of these things are built into the tool. And so we wanted to evaluate how does this stuff actually work among students and researchers who would be working in such a context. So we ran a randomized study, basically comparing Think Causal, BART cause, which is the R implementation of the models I've been talking about, and a condition where people could just choose what to do. So as I said, students would come into our lab. I say students because most of them were current PhD students or master's students. Some were also alumni. So they would come into the lab and they were randomly assigned into one of 3 conditions. They either got Think Causal, which is the point-and-click software, they got BART cause, which is the program software, or they chose their own adventure in the sense that they could use any software and any method they wanted to. They could use Python, they could use Stata, they could use SPSS, they could use linear regression, propensity scores, whatever they wanted to do. Now, these numbers aren't exactly the same for each group because it was actually a block randomized study. Some people didn't know R, and if you don't know R, you can't use BART cause. So we did some blocking. We had a pre-study survey to determine this information. We basically assessed people's R programming capacity. And if they knew R, they had a 1/3 chance of getting think causal, BART cause, or this choose your own adventure. And if they did not, it was a 50-50 split between think causal and choosing your own adventure. So that's why the numbers are not equal between the three groups, because of this blocking. So let's take a look at what people actually did when we didn't tell them what to do. The most common use was linear regression. And beyond that, we had a lot of folks doing propensity scores. Some people actually, 2 people actually knew about think causal and used that. And then 1 person knew about BART cause and used that. But so the vast majority of folks are using linear regression or propensity scores, with a few actually knowing about the software we have. Covariates in our analyses, we collected all sorts of socio-demographic information, basically what master's programs or PhD programs are people in, how many years of education, what field, major programming, years of statistics courses. And the outcomes we wanted to look at were the accuracy of estimates, the time spent on the analysis, and the general user experience. So I'm going to end by going over the results. And so when we look at the distance between the estimate and the true average effect that we wanted to look at, now we want this distance to be small. We want a model that is going to give us an estimate that's really close to the truth. So here, lower is better. And we see that think causal estimates were very, very close to the truth, but there really was not a difference between BART cause and people doing linear regression and propensity score matching. Now, if we do a more formal analysis, we see exactly that. So think causal on average gave estimates that were about 0.2 standard deviations closer to the truth, whereas BART cause and choosing your own method were indistinguishable. Now, we don't just care about point estimates. A big part of this talk has been thinking about uncertainty. We want our intervals to cover the true average effect, our uncertainty intervals. And so here's the percentage of coverage, conditional on condition. And so those in the think causal condition, the vast majority are covering the truth. I believe it's around 90%. Whereas the BART cause and choose your own adventure conditions, less than a quarter in each condition were actually covering the true average causal effect. And if we look at a comparison between these things, we see that think causal causes about a 75 percentage point increase in coverage, whereas there's no difference between BART cause and choosing your own methods, which you could really think of as linear regression and propensity score matching. Actually, let me just go back to this before we finish. So where we're at with all of this stuff is, even though BART has these theoretical properties, this research shows that it's not enough to just put stuff in an R package and say, let it rip. There's this whole implementation assumption piece that is really, really important. And the model underneath think causal and BART cause are exactly the same. But as we've seen in the last few plots, when they're actually used in practice, there's a considerable difference between the two. And so scaffolding methods and building methods that are more accessible makes a massive difference in terms of actually utilizing and leveraging the strengths of the method. I want to thank my collaborators at NYU who have been a big part of the work that I've talked about today, most notably Jennifer Hill and Vince Dory, who I've worked closest with, and Mark Scott and Joe Marlowe have also been really instrumental to all of this work. And I want to close by saying thank you all for your attention. It's been really great being able to speak here, and I've reserved some time for some questions.
Thank you. I'm sure there's many questions, so please feel free to ask me while they're thinking of questions. Would you mind showing?
Yeah, exactly. So I'm not connected to the Wi-Fi, so that's why I kind of skipped over that. But let me just try to connect really quickly, and then I can actually show the software.
Right.
Yeah, I kind of audibled that part given our Wi-Fi problems. Let me see. Should be able to connect to EDU route. Yeah.
Well, while I do that, please think of all your questions, all your present questions about causal inference and everything you've always wanted to ask about causal inference. Reference groups. So, it's 1, 2, just while these.
Yeah, I can take a question while I'm trying to load this out.
Okay, sure.
There we go. Yeah, so why isn't BART cause overfitting? So that is a I didn't have too much time to talk about the mechanics of how BART models work. So usual machine learning methods. You're fitting these optimized trees, and you have to do a bunch of what's called tuning to prevent overfitting. So you usually look at how things perform on some training set and then some testing set. And based on that, you kind of know how much you're overfitting and try to guard against it that way. Why don't we have to do that? So in Bayesian analysis, there's something called a prior. And in this case, the prior is actually what's preventing from overfitting. So how BART cause grows the trees is it's actually not fitting trees to the data. It is randomly generating a tree. So it randomly generates a tree and says, does this tree fit better than the last tree? And with some probability, if it improves the fit, it says, we're going to keep this randomly generated tree. And it's going to do that a lot of times. And that's what the Metropolis Hastings algorithm is doing. And these Bayesian approaches, they use simulations. So you basically do 2,000, maybe even 10,000 runs of this thing. And the software right now, it codes how many, all this stuff is done under the hood, but it cycles through all these iterations of just saying, hey, let's change this tree. And if the change is good, we're going to keep it. And if not, we're not going to keep it. And there's a bunch of properties of Metropolis Hastings algorithms that we know exist that know that over time, it's going to converge to optimal trees that are not overfit. So the Bayesian piece is what protects us from overfitting here. And that's the big innovation of BART compared to other machine learning approaches, is that instead of relying on tuning parameters to prevent overfitting, we're using this Bayesian prior piece. I don't know why my edu Roam is not working today. Oh, at NYU, it just works with that. That would probably be why. It seems to like this better. If this doesn't work, I can show the development version that's on my computer. That's very, very similar to the link. Oh, yeah.
And this BIRT is useful?
Yeah, so this is not built into Think Causal yet. It's one of the things that's on the development branch that we're hoping to merge in soon to the software. So if you have an unmeasured confounder, the stuff I've showed today is not going to help you. That's why I said we're making this really strong assumption. And the model can't fix that. So really, all of this modeling stuff says, if the measurement piece is satisfied, we'll take care of the parametric piece. Like BART cause does not make any parametric assumptions, so it'll take care of that, but we can't fix the structural piece. Now, what can you do with the structural piece? Another benefit of BART cause is it's one of the few machine learning methods, to my knowledge, it's the only machine learning method. I want to emphasize, to my knowledge, if somebody's written a paper about this, I apologize. But it's to my knowledge, the only machine learning method that can be embedded in what's called a sensitivity analysis. So whenever you're doing an observational study, you should do what's called the sensitivity analysis. And what that means is it says, let's suppose that we missed a confounder. Now, how big would this confounder have to be? And here big means how related would it have to be with the treatment, and how related would it have to be with the outcome to change our results, to flip the sign or to change the magnitude. And so you can embed BART cause results within a sensitivity analysis. I'll send you the book chapter that I wrote with my colleague Jennifer Hillenvin-Story, and we have an example of the sensitivity analysis. Right now, it's only accessible through an R package, but we are working on embedding it into the software that I will just show the development version of that is very similar to the actual version. So you'll get a sneak peek at the changes that are coming. So all of this, what I'm about to show, is accessible on a link that I can disseminate, that when you're connected to the Wi-Fi will work.
I'll just connect them.
Oh, okay. Yeah. That'd be great. Yeah, I'll keep taking questions, and then we're going to swap out computers, and then I'll show the real version of the software that you can all get access today. So in the meantime, who has the next question?
Yeah, as your question, some of people research question on how I identify all of the potential confounders.
Yeah, so that is, how do you know what a confounder is? So there's two steps of this. There's a theoretical piece that generally literature has a good idea of what a confounder is. In practice, with bar-cause, really you should adjust for any variable that is pre-treatment and is predicted of the outcome. So any variable that is predicted of the outcome, you should adjust for. And that could sometimes mean all of the things you can measure that are not post-treatment variables. So if it is a pre-treatment variable, and if you believe it has any chance of predicting the outcome, put it in, and these things will handle variable selection for you. So they'll handle variable selection for you. And where is the mouse on this? Oh, right here, it's connected here. So this is actually not the link. This is we're making a website to talk about the software. So just here is the link. Okay, so here's the software. Here's what it looks like. Yeah, so the idea is we have this learning piece where you can learn about causal inference. I'm really only going to focus on the analysis piece. So if you have a data set on your computer, you would click on this and you could just go to wherever it's stored and load it in. I don't know if there's any data on this computer, but fortunately for us, we've built in an example data set for such emergencies. So if I was a researcher, I would have my CSV or my SPSS file or my Stata file. It takes all these types. If you're working with Stata, you can just read in a Stata file, and I would read it in. So here's the data, and I can just navigate through the whole process of doing a data analysis. So at first, I'm going to have to tell it, well, what's my treatment? So this is a jobs training intervention. This data set, very famous in the causal inference world. It's called the Lalonde data set. So the outcome of interest was real income in 1978. And I'm going to have to tell it what my treatment is. Here, the treatment is just called treat. And it means that if you're treat 1, it means you got the jobs training program. And if you're treat 0, it means that you did not get the program. This actually happens to be a completely randomized experiment. So I'm going to go pick a completely randomized experiment. Why do we ask about the study design? Well, dependent on your answer, it's going to start doing a bunch of different checks. So throughout this entire process, under the hood, we're doing a bunch of checks to make sure that you're making decisions that make sense. And if you make decisions that don't make sense, you're going to get a lot of errors that pop up and say, hey, are you sure you really want to do this? Here's a button that will take you to a learning module that will explain maybe why it's not a good idea. And so we can see all of these folks in the treatment group, and we're missing their potential outcome. We're missing what would happen to them without the treatment. And we want to fill this stuff in. So we're going to continue. So how do we select variables? And this is kind of related to your question. Now, there's not a lot of variables in this data set. None of them are post-treatment. So I'm just going to want to adjust for all of them. Now, the nice thing about these methods is, generally speaking, people are nervous to adjust for 300 variables. Because if you do that in linear regression, people might say, well, I'm probably overfitting. Because of the Bayesian piece and because of how these regression trees work, you're not going to overfit if you adjust for a lot of things. They're designed to be able to adjust for all of these variables to satisfy the parametric piece without making parametric assumptions and without overfitting. That's another reason we really like BART, and the research more in the machine learning area suggests why BART is so good at making predictions is because it does the most sophisticated, it has the most sophisticated process of preventing overfitting. The model itself is actually inherently hedged against overfitting because of the Bayesian priors. So I'm going to adjust for everything here. Want to point out, we have spaces for post-treatment variables and like an ID variable. If you have like a variable that's just like an ID number, don't adjust for that. If you have post-treatment variables, really don't adjust for those. I don't have time to cover it today, but we have a whole learning module on what post-treatment variables is or are, if you want to check that out. So I'm just going to save this and continue. And so here is our data. So oftentimes, when you're going through the research process, variable names are encoded as like X1 or PHQ_789. And that's all great, but sometimes we want to change the names. So if I wanted to change these names to something a little bit more sensible, I could do that here. Like if I just wanted to say treatment, I can change treatment, and we can see that I'm actually updating my data as we go. Maybe I want to change this to something like outcome, and it's going to change it as I go. If I do things that I don't like, I could reset all these changes. We're under the hood, we're going to have really intelligent guesses at variable types for all of these things. If you want to override it, you can. And we also screen for missingness. At this point in time, we're just list-wise deleting all missing data. In the future, we would like to build in some more complicated imputation process, but all this takes a lot of work. And there's even some theoretical pieces on the data imputation process that we're still working on doing too. So with this project, the theory and the implementation are happening at the same time a lot of the time. So some things are waiting to have a more stable theoretical approach, so we can say, hey, cite this paper. This is why we're doing it this way. But so I'm not going to change any of our data types. A nice thing about BART is, unlike linear regression, the data type decision is also less consequential. Like if you have something like years of education that maybe in linear regression you'd really want to code as a factor, even if there's some nonlinear relationship and you keep it numeric, because BART's inherently nonlinear, it's not going to make a difference. So we'll just keep going. These are what's called balanced plots. It's a useful way to just baseline, see if your things are similar or different. So this is just a baseline visualization we'll have, but you could do any standard visualization. If you want to look at distributions of all your covariates, you could do that with histograms. You can group it by other variables. So if you want to look at variables between groups, this is a randomized study, so we expect all this stuff to look pretty similar. If it was an observational study, it wouldn't. You can also download all of these plots if you'd like. So you can do histograms, scatter plots, all of kind of the classics. This page we're actually changing in the development branch. It's going to become much more simplified. So that's an exciting thing we kind of have in the pipe. But this is another diagnostic for something called overlap. Basically, you just want to see that for all the area of red we have, there's also some area of blue. Doesn't have to be the same. We just want kind of somebody in that area. Again, it's just like a visual diagnostic. And then I'm just going to plug in a few things. Beyond the scope of today's talk, there's different types of average treatment effects, and they're called sample, conditional, and population. For here, I'm just going to focus on the sample. Right now, this is not something you should worry too much about. I want to estimate the average treatment effect, and I don't want to specify any. These are basically moderators. I don't have any theory to suggest that I have a specific moderator in mind, so I'm not going to worry about it. And then I'm going to fit this model. And now it's fitting my BART model for me. It's going to take me to the results. And this is really the whole process. So my average treatment effect, it's about $1,521 US. 95% CIs, they don't contain zero. Something that also I didn't talk about in the talk, but I really like about this stuff, philosophically, because this is Bayesian, you can interpret there's a reason we say CI, it's technically a credible interval. If you know kind of the difference between frequentist and Bayesian inference, anybody who's ever taken or taught intro stats class knows how it can be really tricky to think of like, what is a confidence interval? It doesn't really mean confidence. It's the whole, well, if we imagine infinite theoretical intervals, 95% of the intervals will contain the true parameter. So Bayesians don't actually think that way. We actually think that you can interpret confidence intervals as actually confidence. So you could say that we're 95% confident that the average treatment effect is between 575 and 2,454. So here's just our kind of summaries of the results. The thing I think is the most exciting is, as social scientists, there's a lot of interest in treatment effect heterogeneity. So this plot, we call it a waterfall plot. And this is each person's predicted treatment effect. So each one of these points is an individual in our data set. And the kind of shaded region is the uncertainty for each individual. And so what this tells us is the folks over here seem to have a higher treatment effect than the folks down here. If this line was exactly flat, it would mean that there's no treatment effect heterogeneity. And the more jagged this line is, the more curved it is, it means the more treatment effect heterogeneity there is. Now, I don't know what is predicting this heterogeneity. I don't know which variable is kind of driving these differences. And so if we go to predictors of variations, we're going to fit a simple regression tree on those individual predicted effects. And it's going to give us a nice starting point of where to look in terms of moderation effects. And so here, things at the top of the tree explain the most variance. And so we see U74, which it means unemployed in 1974. That's what this variable means. And so how I like to do it, I like to start at the top of the tree and look down for kind of relevant things. So when I actually want to look at exploratory subgroup analyses, I'm going to start with that U74. So U74, let's fit it. And now it's broken up our average treatment effect, conditional on if you're unemployed in 1974 or not. Notice now the x-axis becomes the CATE, the conditional average treatment effect that I talked about during the talk today. And so if I scroll down, we actually look at the effects. We'll see that folks who are unemployed in 1974 have a much bigger impact from this intervention than the folks who weren't. If you're unemployed in 1974, the average treatment effect for you was about 1,760, and if you're not unemployed, it was only $800. So it's almost twice the effect for folks who are unemployed before. And so that's basically what an example analysis would look like using the software. Like I said, this is still it's still kind of in beta mode, meaning that we're unrolling a lot of new features still. And so there's a lot of exciting stuff we have planned that's going to be coming out in the following weeks. But even this version, which is what we used for the study, is already showing really big performance increases over using the approach purely in R.
Study with repeated measurements of one. Oh, if I have a study of repeated measurements with with every individual,
Yeah.
How would I incorporate that? So would I put ID into it, or yeah?
Yeah. So if you have repeated measures, so this is one of the areas where like the theory stuff is still coming out. It depends of is it at like time point 1, nobody gets the treatment, and then at time point 2, everybody gets the treatment, something like that, or like my answer would depend on the repeated measures. Repeated measures is not in here yet because we're still thinking through some of these issues. And the answer is it depends on what type of repeated measures is the short version. Yeah.
Clustering. So
Yeah. So if you have clustered effects, we actually wrote a paper on this. So if it's clustered effects, you can fit a random intercepts model. So let's say if I go back to causal question, I could include a random effect. And if I say yes on the variable selection page, there'll be a bin for model as a random effect. And our team wrote a paper. It's in Entropy, Google. It's called Stand for BART. It's free, open access, so you can read about it there. But we've embedded the random effects frameworks into this. Right now, we only allow you to model a single random intercept in Think Causal because we're actually still doing some studies about there's a lot of ways to specify those types of models. And even when we wrote that initial paper, we kind of punted on some model specifications. If you read the paper, one of the things we found is even if you misspecify the random effect, BART will still do a really, really good job. And so we're still trying to find out how much wiggle room do we have with the random effects misspecification. And ideally, if it's as much as we think there is, we want to make it easier from a UI perspective. But until we're really sure of that, we're hesitant to allow people to access the full like random slopes features. Because we basically to review a little bit, we don't think modeling random slopes matters too much in our framework because the BART piece will learn any existing random slope. And so if that's true, we just want people thinking about random intercepts, because if you don't really know about how the multi-level frameworks work, you can start making strange decisions pretty quickly. But so we're kind of holding off on that for now. But if you know R, you can use Stanford BART and do any type of random effect specification you want. And if you want to look into that and you have questions about how to do the R stuff, happy to correspond over email about any implementation problems you might have or questions. But that's actually what I was thinking for the repeated measure. Depending on the type of repeated measures, you could use Stanford BART, which is our multi-level generalization of this. And just Google Stanford BART or web search Stanford BART, and it was written in Entropy in I think it was released in, I want to say 23, it may have been 22. We wrote it in 22, the publishing stuff. I don't remember the year it actually hit the publisher.
Does think causal handle binary outcomes and
Yes, it handles binary outcomes automatically.
multiple treatments?
Multiple treatments we have not put in yet, but we just got a grant actually 5 days ago to build multiple treatments in. So that is coming very soon. So in the next year, we'll have multiple treatments built in. And the grant is actually very exciting. We're doing a lot of stuff we're really looking forward to in the BART piece that will allow this to become even more powerful. And we're doing a lot to shore up the exploratory stuff. So basically you can do exploratory moderation in a way that you can feel better about it. And same thing with multiple treatments. So we're specifically addressing some of the multiple comparison issues that arise. So you can kind of jointly do all of it. And so we think it's very exciting, but coming soon. But it's something we're thinking a lot about.
In my research, I found some variables may affect both the outcome and the recruitment. So I think I should put them into my regression model. But sometimes I was educated that I should not put them into my regression model. I'm thinking, is there any reason for not including them in my regression model, and why I should not?
Yeah, the only reason you shouldn't include it in a regression model is if it is a post-treatment variable. But if it's an observational study, even there's a paper by Paul Rosenbaum in 1984 about this, that even if it's like a little bit post-treatment and it's still like you think it's a really big confounder, you should still adjust for it because the confounding risk is worse than the post-treatment risk. And these are very like the example for this is a lot of the propensity score work was done using a data set called the IHDP data set, like the Infant Health and Development Program. It was basically a preschool program. And they weren't able to measure parents' income until a year after the intervention began. So income was technically post-treatment. And when I say post-treatment, the things you really want to look out for is, could getting the treatment influence people's income? And Rosenbaum basically did a bunch of work showing that like the confounding risk is still bigger than the post-treatment risk. The really problematic post-treatment variables that will really wreck your analysis and you should not adjust for is intermediary outcomes. So say if my outcome is verbal reasoning scores at age 6 and I have verbal reasoning scores at age 5, I don't want to adjust for the age 5 one if the treatment began at age 2. And why that is, if you think about what adjustment's actually doing, you're adjusting out the whole treatment effect. Because if the treatment actually works, you'll see a big difference in verbal reasoning at age 5 between the treatment and the control. And when you adjust for that and you're kind of trying to squeeze it equal and you're saying, well, let's look at people that have the same verbal reasoning between the treatment, it basically regresses out the effect. But so if it's not one of those like direct outcome post-treatment variables, I disagree with that advice. A lot of that advice, and I did a bunch of qualitative work on the software where I had folks come into the lab and use the software in front of me and I would ask them questions. And this is actually related to what happened with BART cause in our study. Like what, if it's the same model under the hood, how come think causal is doing really well and BART cause is doing pretty bad? And what we found is a lot of folks did not adjust for all 58 variables. And we told them they were all pre-treatment. Like we said, these are pre-treatment variables. And a lot of folks only adjusted for about 10 or so. Now, why is that? In the qualitative work I did, this would happen too. And I would ask people and they would say, well, I was told not to adjust for things. And I would ask them like, well, why were you told not to adjust for things? And a lot of people would say that in like intro stats, they were told they would overfit. We don't have an overfitting problem. So because we don't have an overfitting problem, if you should definitely adjust for it, is the take. And so in Think Causal, if you click observational study and you don't adjust for variables that aren't dragged into post-treatment or ID, they'll say, hey, we noticed you didn't adjust for like insert, like if you didn't adjust for 10 variables, say you didn't adjust for these 10 variables, like for an observational study, you really should do it. And then we have links to the reading where you can read about why. But so that's my take. Yeah, and check out Rosenbaum 1984 about post-treatment variables. That's a post-treatment variable one. The other thing too is to give a more detailed question. There's two religions of causal inference. So the talk I give and the framework that all of the research we do is rooted in what's called the potential outcomes framework of causal inference, which was initially described by Don Rubin. There's another framework called the DAG framework of causal inference that sometimes makes contradictory claims about particularly variable selection. If you're familiar with structural equation modeling, that's kind of where that camp comes from. And they disagree with us a little bit about variable selection. The reasons why I don't have time to get into, but that may be another thing you've been told about. But that framework, like I said, different set of assumptions and all sorts of other different things. This is more common, the potential outcomes, particularly in education and social science, is the potential outcomes framework, particularly economics.
Questions?
Question, we're comparing apple and oranges. But for example, in the health area,
Mhm.
a lot of times the randomization of observations is very difficult. And people often, or many people, use propensity score to adjust it. The question is, if someone if you're in your model, you're pretty sure about what your confounding variables are, okay, maybe obviously the things that you can think of, and is this still a practically good studies if you continue to use propensity score versus using more like mining type of software like this?
Yeah, so what to do about propensity scores? So at the end of the talk, I thank my collaborators, particularly Jennifer Hill, and I think it's important to note that a lot of Jennifer's earlier work was on getting people to use propensity scores. Jennifer says that the first 10 years of her career was trying to convince people to use propensity scores, and the last 15 years of her career has been trying to convince people to stop using propensity scores and use machine learning. Propensity scores work when done properly, and all the problem is when done properly. So if your propensity score model is specified appropriately, propensity scores work for average treatment effects. Propensity scores don't do well with heterogeneous treatment effects. It's just by virtue of how they work, they're kind of unable to do that in an efficient way. So this is the machine learning approaches are really kind of the only game in town for really particularly exploratory moderation effects. But for average treatment effects, propensity scores work. Now, how can you do, if you are doing propensity scores, what you should make sure to do is to check balance statistics for every moment of the distribution. And that's where people usually go wrong, is they'll only look at means, or honestly not look at things at all. They'll just fit like a logistic regression propensity score model and then kind of move on with the analysis. So all of the work on propensity scores kind of assumes that you have balance across all these moments. And so for this data set, for the data set we did in our study, you theoretically could get the correct answer with propensity score models. Now, how would you have to do that? You would have to fit a flexible propensity score. So if you use like a machine learning approach to estimate your propensity score matching still can work pretty well, but you need to use a really flexible approach to estimate the propensity score, which a lot of folks aren't doing. If you want to read more about it, My colleague Jennifer Hill wrote a paper in 2011, which is actually the first BART for causal inference paper. And she directly compares BART to propensity scores and kind of talks about the advantages of why we think this framework is an advantage over propensity scores. But I should say there's a lot of sometimes like journals are really insistent on still using propensity scores, or there could be a lot of reasons why you still are using propensity scores. And if you are in that world, I would really recommend using a flexible estimator to fit your propensity scores, like using a machine learning model to fit the propensity scores. There's a lot of packages in R and Stata that will do that for you. There's something called Twang for propensity score modeling that's really good. You could use BART to fit your propensity score. You could use other machine learning approaches. And really, it'll learn the value of that is it'll learn those more complicated moments for you, particularly the variance in the covariance piece.
Okay, I'll look for Jennifer Hill's article. Thanks.
Okay, questions? No, really like to thank Professor.
Yeah, thank you. Yeah, thank you all. I really appreciate the invitation. Yeah.
Thank you.